All right, so in that meeting, we chose the dates, and I got my dates down, but rather than trying to say them to you verbally, I'm just going to tell you a couple weeks after we get back from break, we're going to be starting our practice exam. It'll be Thursday and Friday, A day, B day that week. We'll be doing the free response questions on that Thursday, Friday. So A day will do them on Thursday, B day will do them on Friday. And then the following Monday and Tuesday, we'll do the multiple choice. And so again, A day will be on Monday, B day will be on Tuesday, and that'll be the multiple choice part of the exam. And it'll be a practice exam. The free response part will be the same length as normal. And unfortunately, you will only have 80 minutes instead of 90. So it'll be more drastically curved because you're being cut 10 minutes. So the multiple choice part actually has fewer questions. And so it should be good for 80 minutes, but either way, I always use a steeper curve than the actual exam because of it's your first time, you're having to do it on 2 different days. And so, but that'll be your actual final exam grade. So before you take the AP exam on May 5th, you'll have your final for this class complete, right? And you'll know what your score is. And then after we take the AP exam, there's going to be I'm kind of playing around with some different ideas. After our meeting yesterday, I found out that we have more flexibility than I thought. So, and I'll talk to you more about that next week. But what we're going to be doing, I think, is giving some options for, hey, if your lab grade's a little low, here's some labs you could do to boost that up. Hey, if your positive physics grade quizzes are a little bit low, here's something you can do to boost that up. Hey, if your final exam turned out a bit low, here's something you can do to boost that up. So I think we'll be doing more things like that. I originally thought maybe we'd do a little bit with waves and electricity just to introduce those topics. But then when I was looking at the dates, the first week after your exam, that's still AP exam week. And so many of you will be taking other AP exams. And so covering anything of any great detail will be sort of a loss for quite a few of you. And then after that, we've got 1 week in exams. So it's like, okay, maybe we don't really have time to do that. So I think we're just going to do something a little bit different. Yeah.
When was the first AP exam again?
What, ours for physics?
Yeah.
May 5th. It's Wednesday, May 5th.
It's my birthday.
So, oh, happy birthday. What a way to celebrate.
That's hype.
All right. So in terms of the flow, the way it's going to work in class is we're going to finish, hopefully, momentum next week. And then we'll probably take 1 day to talk about pendulums, which is another example of simple harmonic motion. We've talked about circular motion, rotation, and mass on a spring. Those are, yeah, and then pendulum is the last bit of simple harmonic motion. So we'll cover that the first day back. And then we'll pretty much just have 2 or 3 class periods just to review, practice, and then you'll take your exam. And then we'll have 2 or 3 periods after that to just review how you did on the exam and explain the questions that were on the exam and practice further. So that's kind of what we have left.
So
yeah,
you're giving us our final before the AP exam, and that's like our mock AP like practice exam?
It'll be your practice exam and it'll be your exam grade for this class.
Dang.
It always is more intimidating than the reality. Students always are very, they feel pretty nervous, but then after it's over, they're like, oh, it wasn't as bad as I thought. Yeah, we'll spend several days reviewing, and then we'll take it. And then afterwards, we'll spend a couple more days reviewing because you'll have it back. You won't be able to keep it because it's secured information, but you'll be able to see it back and work through, oh, here's why that answer is what it is, and here's how you solve it, and kind of get your questions answered. So
like from there, we do like a mini correction kind of on it.
Yep.
So like as our study.
Yeah, so that's what I wanted. Like I was saying, we'll, instead of covering waves and electricity, we'll do more like corrections to improve your grades. Yeah.
And they just won't see it.
All right. Yeah. And some years past, I've let students take the practice exam twice because I have a couple different versions. I have several different versions. But I just looking at the times and when we have, there's just not really time to do that unless we do a Saturday. And all the Saturdays were already booked by other teachers because that's the only time they could do it. And so I feel like instead of that, I'm just going to give you a chance to redeem some of the points you missed instead of giving you a second chance. So
thank you.
We'll just kind of adjust. And we had to do a lot of adjusting this year, so we're just going to take it to adjust. in the end, if you all get A's in my class, then I'm happy. I'm not trying to hold any back from getting an A, so I'm happy to give you an opportunity to try to earn some of those points back and improve your score if you need it. But all that to say, you should have received an email in the last few days. We went a little bit off the rails there, but you should have received an email in the last few days from Miss Davis, I think, could have been from Mr. Lindsay, about AP testing. And so make sure you're not throwing that one away. Read through it. It talks about the dates. It talks about what you need to do to prepare. It talks about what you need to do to make sure you're registered properly. And if you are not taking it on May 5th, if that's not possible and you're going to take it June 9th digitally from home, you have to tell them, because if they don't hear from you pretty soon, they're assuming you're taking it on May 5th and they're buying the test for you. And then if you tell them after they've already bought the test for you, you have to pay for both. So you want to make sure that if you're not taking it May 5th, you tell them as soon as possible. And there's an application process. You have to give good rationale for why you're not taking it on May 5th, because they're assuming everyone's taking it on May 5th. Even if you haven't been coming to campus, they're assuming you're taking it on May 5th, that you will come that day. So if that's not your plan, that's okay, but you have to communicate that with them. And that's what the email talks about. So make sure you find that email and make sure you do whatever you need to do to take care of that. So, all right, I think that's it for that. Reminder, Positive Physics Unit 13 assessment, that's due tonight, the energy one. And today we're just gonna wrap up the energy unit. We're gonna practice more with work energy theorem. We're gonna also practice torque from last unit. We're gonna go back to power. We defined it the first day of this unit, but today we're gonna look at some equations and potentially, if we have time, practice a couple problems with that as well. Any questions? All right, so let's go ahead and try our practice torque problem for the day. We're going to continue to practice these daily leading up to spring break, at least. I don't know if we will after spring break, but. All right, so here is your latest, greatest. If you have worksheet 2 from the last unit, it's the same. We've already done at least one other problem, maybe a couple, I can't remember, from that worksheet. This is question number 2 from worksheet 2. So you can obviously see it on the screen, and you guys in the Zoom, you're seeing this on the screen, right? The problem with the truck is making sure it's shared properly. So if you want to write it on the worksheet 2, you'll know you're at the right place because the worksheet has the same picture of the truck. If you just want to look at the screen and solve it on your own paper, that's fine. But let me read it to you, and then we'll give you several minutes to work on trying to solve it. So it says, workers have loaded a delivery truck in such a way that its center of gravity is only slightly forward of the rear axle as shown in the drawing. The mass of the truck and its contents is 7,460 kilograms. Find the magnitude of the forces exerted by the ground on A, the front wheels, and B, the rear wheels of the truck. So you can see in the picture, there's the center of gravity. The rear wheels are 0.63 meters from that center of gravity. The front wheels are 2.3 meters from that center of gravity. Your 3 steps again are, first, forces, then point of rotation, axis of rotation, find that pivot point, and then torque. Then torque. So force, pivot point, torque. All right. Take a few minutes, see if you can solve this one. In the Zoom, when you get an answer, go ahead and type it in the chat. Anybody in the classroom have an answer yet? Oh, 1, 2. What'd you get? Got a few people done here in the classroom. If you're in the Zoom, as you finish, if you're able to, go ahead and put some answers in the chat so we can compare. If we're coming up with the same and different results.
Sure, what is this? It's like black stuff. Is it like silicone or tape or something?
I don't think it's double-sided tape.
It's pretty strong.
It's probably like the double-sided Gorilla tape. It's like thicker and
Double-sided electrical tape. Looks like.
Yeah, that's what I'm thinking because it does look like electrical, but
yeah,
it's not as like strong as electrical.
yeah. There's I mean, it may not be Gorilla brand, but I've used Gorilla tape before, and I've heard of Gorilla glue. It's like super glue, but there's Gorilla tape. It's like kind of like duct tape, but way stickier.
Yeah, that's what this seems like, because electrical tape would just.
Yeah, so they probably just got some double-sided tape like that. Is my assumption.
Cool.
Give about 1 more minute to try to wrap up. I was watching the video later. What are they talking about?
Well, gotta throw in a few curveballs.
Yeah. All right, so let's kind of talk it through. If you do have answers, you can check. If not, you can kind of follow along and finish up and ask questions as we go. I want to make one quick comment. You can choose your pivot point anywhere because this is a torque balance question. Anytime the torques are balanced, meaning that there is torque, but there's a net torque of 0, so the object doesn't actually rotate. You can choose your pivot point at any spot. It may be easier or more complex depending on what you choose, but you're not limited. Now, if it is actually rotating, you should choose the actual axis of rotation. But if it's a balanced torque problem where there isn't any rotation, you can use any pivot point. Now, just because there's no rotation doesn't mean there's no torque. It just means there's no net torque, right? So if this truck were made of paper, it wouldn't be strong enough to hold the torque in the middle between the wheels, and the paper bed would collapse between the wheels, right? So there is torque regardless, but it just doesn't cause rotation because it's balanced torque, all right? So let's take a look. I'll show you how I set it up, and I'm pretty certain that most of you probably did not choose the method that I did, but the method that I chose is to show you a type of problem solving that can be very helpful, not necessary for this one, but very helpful for other problems with torque and with energy. And so I want you to at least see it. And by no means is it the only way to solve this one. So the basic premise though is going to be the same. Like it's not going to stray very far. It's just a matter of where I chose my pivot point. Probably most of you didn't choose the pivot point I chose. All right. So if we look at the forces, that's our first step. We've got the normal force of the ground on the rear wheel. We've got the normal force of the ground on the front wheel. We've got the weight of the truck at the center of gravity as marked on the picture. And then I chose my pivot point to be at the center of gravity. Okay, so if you chose that, that's great. You did the same as me. If not, most students choose the rear wheel. Okay, and that's fine. That's actually mathematically a bit easier if you choose the rear wheel. It's a wise choice. But I want to show you this other method. If you choose a different point, you can still solve it with a little bit of not too complicated algebra, but something you might not have thought of before, or at least not in this context. So here's my force equation. The upward forces of the normal force on the rear wheel plus the normal force on the front wheel are balanced by the weight force, the only downward force. So there's two upward forces and one downward force. I know the truck is not going to fly into the air or dig into the ground, so it is going to be balanced in terms of force. The only force that I can calculate, though, is the weight of the truck. And I just used 10 on my example here. I used 9.8 on my paper, but I used 10 here. So 74,600 newtons of weight for the truck. Now for my torque, I know that since I chose the pivot point to be in the middle, the weight of the truck would not cause any torque because the weight is right at my pivot point. So its R value is 0. It has no distance from the pivot point because that's where I chose the pivot point. So there is a distance for the rear wheels and there is a distance for the front wheels. So those two would be causing torque. And because they're both going upward, but they're on opposite sides of the pivot point, they're actually fighting each other. If the truck could spin around the pivot point that I chose, the rear wheel force would make it go clockwise and the front wheel force would make it go counterclockwise. Now we know it doesn't spin around that spot, but if it could, that's the way it would go. So those two forces are creating opposite torque. So they have to be equal and opposite because the truck doesn't actually rotate. All right, so then if I start plugging in some information, I know the rear wheels are 0.63 meters from where I chose my center axis of rotation, and the front wheels are 2.3 meters from where I chose my axis of rotation. That means I don't have the ability to solve for either of them in the way I set it up. Okay, but I can find a proportion. I know that the rear wheel force is going to be 3.65 times the front wheel force. Just solving for FR, right? Taking 2.3 divided by 0.63. Now, because I know that, I can put that back into my force equation to show that, well, this FR is 3.65 FF according to this. I'm just substituting that in for FR. And then I'm leaving the front wheel force as is, and I know the weight. So now, because I'm substituting this in for FR, I only have one variable. All right. And because I only have one variable, I know that's going to be 4.65 times the force of the front wheels equals the weight. And if I solve that, I get about 16,000 newtons of force on the front wheels. And then I can plug that back into the same equation. Now I know the front wheel force, so I can solve for the rear wheel force. And it is about 59,000 newtons. And so you get a little different if you use 10 versus 9.8, but you should get pretty similar results. Any questions about how to solve this problem? How many of you chose the back wheel as your pivot point? Okay. How about in the Zoom? How many chose the back wheel as pivot point? Okay. How many chose the same spot as me? Okay. I'm surprised. Actually, more people chose that spot than I expected. So it's obviously able to be solved. Did anybody choose the front wheels as your pivot point? It makes the least sense based on what they gave us information-wise, but it's possible to do it that way too. And you should get the same answer no matter what pivot point you choose. The one thing that you have to be careful if you choose that rear wheel, and if you got the right answer, then you did it correctly. But I have had students that take the 2.3 as the distance from their pivot point and forget to add the 0.63. So you do have to add those together for your distance of your front wheel if you're choosing your rear wheel as the pivot point. All right, so good. We've got another chance to practice torque under our belts. Let's go ahead and go back to work and energy theorem. And we'll also, like I said, come back to visit or revisit the concept of power today as well. So here we go. First few slides are just going to be kind of a review, a summary of what we've already talked about with the work energy theorem. We're going to summarize it in words. We're going to summarize it in variables and equations. Then we're going to summarize it with some examples. So I'm going to go through it fairly quickly. It's all review. But we know an object's kinetic energy equals the work that was done to accelerate it from rest to its present speed. Now, it doesn't always have to be from rest to its present speed, but in that context, that's how much work would be done, and that's how much the kinetic energy would change. So if we're thinking through our relationships, we can prove, and we will in just a minute, that the work done would be 1/2 mv squared. And that's where the whole kinetic energy equation comes from. Just saying the work done equals the kinetic energy change. So knowing that that kinetic energy is 1/2 mv squared and work and kinetic energy are equal, we know that that's what the work will be as well. So we can use that equation for finding work or finding kinetic energy. But while that's the only equation for translational kinetic energy, that is not the only equation for finding work, right? We can use FD cosine theta for work as well. All right, so an object can have kinetic energy. A system can change configuration. So systems can have more types of energy. So kind of going back to our system flow circles on those bar graph papers that we did. If you put an object in that circle by itself, the only energy it can possess is kinetic energy, because that's the only energy that an object can have in and of itself. If it's got gravitational potential, then you need the Earth in there, because the Earth's force field is what creates that gravitational potential. If you've got elastic or spring potential, then you got to put the spring in there, because the spring is what creates that with the object, right? So you have to have the object and the Earth for gravitational. You have to have the object and the spring for spring energy, right? So you want, if you're going to do dissipated energy, then you have to have the road or the track if there's friction. You have to have the air if there's air resistance, right? So objects can have kinetic energy by themselves, but if they have any other kind of energy, it's got to be part of a system. And so keep that in mind as we look at examples today. You're going to be solving some later and teaching each other the problems you're assigned. All right, here it is a little bit more graphically, mathematically, but the same thing. The work done by a net force on an object is equal to the change in kinetic energy. So another way to look at that theorem mathematically is the net work would be the final kinetic energy minus the initial, right? So just thinking it through by what that theorem means. Now that equation's not on the AP list. The only equation for work, just double check, make sure I'm not forgetting one. The only equation for work on here is right in the middle of the page, right below kinetic energy. It says delta E, change in energy, equals work, equals F parallel D, equals FD cosine theta. So they're just using that here, showing that it's the change in kinetic energy for an object going from rest to a certain velocity. It's something you hopefully can logically think through. I don't necessarily think you should add it to your list of other equations, but I do want you to make sure you understand it. So if it has an initial velocity and then a force is applied, we know net force causes what?
Acceleration.
Net force causes acceleration. If there's an acceleration, what happens to the velocity?
Changes.
It changes. If the velocity changes, what happens to the kinetic energy?
It changes.
It changes. Okay, it's a chain of events, right? And so that's all they're saying here is if there is work being done, there had to be a force applied. If there's a force applied, there had to be acceleration. If there's acceleration, there had to be a change in velocity. If there's a change in velocity, there has to be a change in kinetic energy, which means work was done. We're back full circle. Okay. Yeah, Ethan?
So if there's, like, let's say a ball, and it's rolling down and you push or pull it so that you turn it in like a circle, are you doing work on the object?
To make, so it's rolling down a hill and you,
It's just rolling like constant speed on a flat surface. and
Okay.
then you push it in the right direction so that it turns a perfect.
goes a different
circle.
direction. Yeah. Oh, so you're applying a centripetal force.
Yes.
Okay. So if you're applying a centripetal force actually just keeps it going into a circle, but it wouldn't have a displacement parallel to that force.
Okay.
Yeah.
Yeah, that makes sense because
Yeah.
it's always perpendicular.
Correct.
So no work would be.
So
done.
no work is being done in that case.
All right. Cool.
All right, so let's look at some cases though where work is done. Here like we saw in the definition, we've got a velocity of 0 starting from rest, which means no kinetic energy. We're going to see a displacement of a certain distance. We're going to apply a net force. And underneath here, it's just reminding us of all these equations. The equation down here in the bottom yellow now is a lot more like what you see on the College Board list. But that net force does work as long as it's increasing the kinetic energy of the object. So if we have that net force increasing its velocity, it's also increasing its kinetic energy. But once the net force is released, so if the net force only is applied for a certain amount of time, then that acceleration will cease as soon as the net force ceases. So as soon as the net force is taken away, it will no longer accelerate. If it's going to no longer accelerate, what's going to be true about its velocity? Constant velocity. If there's no longer a change in its velocity, what's true about its kinetic energy?
It's the same.
It's also constant, right? So again, chain of events. The whole part here that I'm trying to emphasize is you have to think about the relationship between all these things. Forces, which we learned last semester, work and energy, which you've just been learning in this semester, acceleration, which we learned last semester. All these things have to be pulled together in your understanding of how they interrelate. Because there are sometimes problems where they'll say, hey, this object moved 20 meters, but the force was only applied for 10. And the mistake a lot of students will make is they'll use the 20 meters to find the work done. But no work's being done in that second 10 meters. Work's only being done as long as there's a net force. As soon as the net force is gone, no work. No work means no change in kinetic energy. No kinetic energy change means no velocity change, constant speed. So we've talked it through in both ways, right? Starting at work and going one direction, starting at force, going back the other direction. Like you can think it through in either direction, but I want you to be really confident with that chain of events, that chain of logical connections of force, acceleration, work, energy, how they all fit together. All right. So here is a quick, and I'm not going to spend much time on this either, but here is a quick summary of where that whole work energy comes from, that theorem, and where the 1/2 mv squared comes from. So if you look at the first box on the left, we can see that there is the third kinematics equation that we learned back in the day. We defined acceleration, we came up with kinematics equation 1. Then we modified it, came up with equation 2. Then we combined equations 1 and 2 and came up with equation 3, right? It was all derived from concepts. So here's this equation. If we're in this scenario where we're starting from rest, the VI is 0. So if we solve for acceleration, it's final velocity squared over 2 times the displacement. And you can see they just changed delta x to d so that it fits better with what we usually see in the work equation. Now they're taking that value for acceleration, v squared over 2d, and putting it into Newton's second law in place of the a. So now Newton's second law becomes m times v squared over 2d. And then that's a force. So now we can put that into the work equation for force, which gives us work equals mass times v squared over td times d cosine theta. And in this case, because it's parallel, cosine 0. And so the cosine 0 cancels, the d's cancel, and we get work is mv squared over 2, or 1/2 mv squared. And because of the work energy theorem, we know that any work that's done shows a change in kinetic energy. And so we can go from kinematics through Newton's second law, through work, and show where this work energy theorem comes from and how it equals 1/2 mv squared. Right, so not something you would have to derive or prove, but kind of an interesting chain of events. If you think about what we've learned this year, this is the sequence we've learned, right? Kinematics, forces, work, and energy. Questions? All right. Like I said, I can't imagine them. I've never seen them ask anything like this to derive this equation. but I think it's good for you to see where it comes from. It also just helps you continue to see how you can manipulate equations, because they sometimes do ask you to manipulate equations, right? Ask you to solve for something, but give you very few, if any, numbers. So good to see those steps. All right, now let's prove the work energy theorem with 3 different forces. First, we're going to look at a force pulling to the right while it's moving to the right. Then we're going to look at a force pulling up while it's moving to the right. Then we're going to look at a force pulling left while it's moving to the right, and see how the force changes in those 3 different scenarios. So first, we're starting at rest, V equals 0. We got a 4 kilogram block, a force of 8 newtons pulling it to the right for a displacement of 10 meters. So what's the work done?
80 joules.
80 joules, 80 newton meters, which is better represented as 80 joules for work, right? 8 times 10, force times displacement. We don't need the cosine theta because the force is parallel to the surface. The force is parallel to the displacement. So it's going to be cosine of 0. All right. So if I think about the work energy theorem, I know there's 80 joules of work. Well, what's the final velocity if it started at rest? Well, work is equal to the change in kinetic energy. So the final kinetic energy minus the initial kinetic energy, and kinetic energy's equation is 1/2 mv squared. I don't know the final velocity, but I do know the initial was 0. And I know now the net work is 80 joules. So I plug in the 80 joules. I plug in the 4 kilograms for the mass. I plug in the 0 for the initial velocity since it started at rest. And I can find that the final velocity would be 6.32 meters per second. It's going from rest to 6.32 meters per second. And we're either assuming that there's no friction or that this 8 newtons is just the net force, one way or another. Probably a 0 friction is what, they don't say it, but I'm guessing that's probably what they're assuming here. But that means it's going from 0 to 6.32 meters per second due to that 8 Newton net force and the displacement of 10 meters. So our work energy theorem showing us step by step. And this is the kind of work you'll have to do often to solve these problems. Figure out the work, convert it to energy, find a velocity. All right. Now, what if the force was straight up? So this is a 40 Newton weight. So 8 newtons is not going to lift it off the table. It's just going to make it feel a little bit lighter, right? But it's not going to lift it off the table. If it starts at 5 meters per second while it's moving across this frictionless surface here, and it has an 8 Newton upward force, how much work is that 8 Newton force doing?
0. None.
None. It's perpendicular, right? So it would be cosine of 90. So if we're thinking 8 newtons force times a 10 meter displacement times a cosine of 90 is 0. So there's no work being done by that 8 Newton force. But in this case, it started at 5 meters per second, so it just kept moving. And again, seems like a frictionless surface here is what they're considering. So work energy theorem, I know the work is 0. I know the initial velocity was 5. So I have everything I need to find that final velocity. And so I plug in 0 for the work. I plug in 4 for the masses. I plug in the initial velocity of 5. And I get that the final velocity will also be 5. So if no work is done, there was no net force parallel to the displacement. If there was no net force parallel to the displacement, there was no acceleration. If there was no acceleration, there is no
Work. Joules.
work. Yeah, but I'm looking for something else.
Change in velocity.
Change in velocity. If there's no change in velocity, there's no
Change in kinetic
energy. Okay, so that same trail, that same process of thought. All right, we just kind of proved it here with the scenario. Last scenario, same 4 kilogram block, moving to the right. This time it's going to come to rest because it's got an 8 Newton force pulling against its displacement. All right, what's the initial velocity? Any predictions?
But it was the first one, whatever that was.
Whatever that first one was, it should be the same, right?
6.32 or something?
6.32, yeah, so let's prove it. So we've got this block sliding for 10 meters. So we've got an 8 Newton force. So there is work being done because that 8 Newton force is parallel to the displacement. It just happens to be in the opposite direction. So 8 times 10 times cosine 180, because those forces are at 180 degrees, right? Displacements to the right, forces to the left. And so that gives us a negative 80 joules of work being done. Now, remember, work is a scalar. So what this negative is telling me is just that the force and displacement were opposite, because force and displacement are vectors, right? So this isn't saying that work is a vector. This is just giving me a representation. Oh, the quantity of work done is 80 joules. It just so happens that the force and the displacement were in opposite directions. That's what the negative's telling. Okay, so don't treat it as a vector. In fact, you can just treat it as an absolute value of 80 if you choose. Now, if we go to the work energy theorem, we can plug that 80 joules in. They've shown the negative sign. I probably would have just plugged it in as 80, and you'll see why here in a second. They sort of just suddenly vanish away, the 80 joules here, because we've got, I guess you could think about it as this negative taking it away too. So mathematically that works, I guess, taking a negative 2 times the other side and the negatives cancel. But we don't even need to worry about that negative necessarily. If you had a negative in the square root symbol in the radical, you couldn't take the square root, right? So sometimes you'll get a problem where you'll end up with a negative, but just remember, hey, work is a scalar. The negative is telling me something about the force, not the work. So if you ever end up with a negative in the radical, don't worry about it when you're dealing with work or energy. And in this case, we find out that the initial velocity was, like we predicted, 6.32. In the first scenario, the force pulling it to the right made it end up with a 6.32 meters per second velocity. And this one, the force making it come to a stop, it had to start at 6.32 meters per second, since the force was the same and the weight was the same and the displacement was the same. Questions? Going kind of fast, but I feel like in some ways it's a bit repetitive, but I want you to see it a variety of ways. All right. So what if we have an actual problem to solve? All right, so this picture looks crazy, but let's break down what it says here. This 2 kilogram object. All right, so we got our weight force going down 20 newtons, our normal force going up 20 newtons.
Just ignore them.
Right? And yeah, we can ignore them, right? Because they're perpendicular to the displacement. But we're drawing everything on here, okay? All right, so, and then it has an initial speed of 5 meters per second to the left. So top up there, purple, initial velocity 5 meters per second to the left. It then moves 4 meters as an external force of 8 newtons, pulls it to the left. So you can see the 4 meter displacement there in black. You can see the 8 Newton force there in red. The force of kinetic friction is 3 newtons. So you can see the friction force going the other way, resisting its motion. Calculate the final speed of the object. Hint, use work energy theorem, right? So I'm going to give you a minute or two, see if you can process this on your own, and then we'll check it out. About 30 more seconds to see how far you get. All right, so a few questions for you. I know some of you may still be kind of wrapping things up, but a few questions to kind of get us rolling here. Sally, as you look at the diagram here with all these forces, what's your net force?
5 Newton.
In which direction?
To the left.
To the left, good. So we've got a 5 Newton net force. Rocky, if there's a 5 Newton net force and a displacement of 4 meters, what's the work done?
20 joules.
20 joules, good. And would it be positive or negative work in sense of direction?
Positive, because it's in the same direction as the initial velocity.
Yeah, good. The force and the displacement are both in the same direction as is the velocity. So since the force and displacement are same direction, we would call it positive work. It isn't that work's a scale, or sorry, a vector, it's just that force and displacement go in the same direction. Good. So those are the first kind of things you should notice initially. And then now we know the work done, so we can figure out using that work kinetic energy, what the final velocity would be like we did on those previous slides. So let's kind of see that fleshed out step by step. Work is going to equal final kinetic energy minus initial. The work is going to be FD cosine theta. Our force, our net force is going to be 8 minus 5, like Sally said, 5 newtons, or sorry, 8 minus 3, 5 newtons. The displacement was given as 4 meters. It's parallel, so cosine of 0. And then for our kinetic energies, 1/2 mv squared at the final velocity, 1/2 mv squared at the initial velocity. And so we can plug in our 5 times 4 times 1 on the left side to get 20. On the right side, we can plug in our 2 kilograms for the 2 masses and our 5 meters per second as our initial velocity. And the only thing we have left variable-wise is the VF. Now it is squared, so we got to make sure we're noticing that. And so we find 20 Newton meters on the left, or 20 joules of work. And then we're going to divide it by, or sorry, add it to the 25 kilogram meters squared per second squared, and then square root it to find our velocity would be 6.71 meters per second. So it does have a net force in the direction of its displacement. So it should be speeding up. And it is. It goes from 5 to 6.7. Any questions? I know I was a little bit short on time. How many of you were able to get that answer?
I was able to get close.
Got close? Okay, good. I know it was pretty quick. I didn't give you a lot of time. Making sense though, the steps were taken?
If the question asked how much work was the pull force doing, would it be 8 times pull, or would it be still 5 times pull?
If it wanted to know the work that the pulling force was doing, it'd be 32 Newton meters to 32 joules. And then the friction would be negative 12 joules. And so the 32 minus the 12 would give you the net work.
Okay, so this is the net work.
Yep. So if you use the net force, you're finding the net work. And if you use the individual forces and then combine them, or to find the work individually, then you can combine them together and find the net work. All right, what if an object is doing something like this?
What?
I'll leave that up to the calculator.
So how do we find out the work in this case? Well, force times displacement times cosine theta is not going to work real well since its angle keeps changing all the time. But if we know its initial and final velocities, we can still find the amount of work done just by using work energy theorem. Since we know that the work is equal to the change in kinetic energy, and we know the mass of the object, and we know the velocity of the object, we can find that if we plug in those 4 kilogram masses and plug in the 5 meters per second as the final velocity and the 2 meters per second as the initial velocity into our 1/2 mv squared portions, we have everything except for the work. So we can find the work done,
Well,
even for an object moving in a very random pattern. Just use the work energy theorem and focus on the energy side of things. And most of the time we've been starting with force and work, right? But you don't have to start with force and work. You can start with the energy side of things and figure out the work.
So the direction of the two forces doesn't matter.
Well, here we're not even using force. And since energy is
The direction of the two velocities doesn't matter.
correct, yeah, because energy is a scalar, so there's no vector component to it at all.
Okay.
Yep. Now, to figure out the displacement, we can't really do that from this information because we know how much work was done based on the energy, but we don't know the force, we don't know the displacement, and it's constantly changing. So we couldn't really go back to those other aspects for this scenario, but we can at least get how much work was done. So here the work done on the object is found without using information about its force or its displacement, or even where the force was applied, or the angle, or the path. Like none of that matters if all we need to know is the work. We can just use energy. All right, last one before we finish up with power. So if we have a 1 kilogram object starting from rest, what is its speed if it's moved 10 meters down the slope? So here we've got, they aren't telling you the angle, they're just saying, hey, it's at such an angle that the weight is 10 newtons down because it's 1 kilogram, and the normal force is less than that because it's at an angle. And so that we could figure out what the angle is, but they haven't bothered. They've just said, here's the normal force, it's 8 newtons. And here's the friction force, it's 2 newtons up the hill. So this, we're just going to use the same thing we've been doing in terms of work energy theorem. We just have to make sure we break that weight force down into components. And the 6 Newton force is parallel to the slope, and the 8 Newton force would be perpendicular to the slope. So I'm not exactly sure why they chose to make this y and this x, but whatever. So the 6 Newtons in the what they're calling y direction actually is parallel to the slope, so it would be doing work. But the 8 Newtons perpendicular to the slope, because of that perpendicular angle, would not be doing work, right? All right. So if it's a displacement of 10 meters, and we know the different forces involved, if we break it down bit by bit based on forces, this x component, this 8 newtons straight down into the ramp, would be FD cosine theta, where cosine of 90 tells us that is doing 0 work. So do you need to write this step out? Not really, but they're just kind of proving to you that those perpendicular forces don't do work. Then if we go to the y, which is the 6 newtons along the slope there, you can see 6 times 10 times cosine of theta being 0, since it's parallel, gives us 60 joules of work. Then if we focus on the friction, friction is 2 newtons times 10 meters of displacement at a 180 degrees compared to the displacement. So that's going to give us negative 20 joules of work. And then for the normal force, it's again cosine of 90, so no work done. So the net work this way is 40 joules. So that kind of goes back to your question, Evan, on the previous question. You can find all the different works, add them together, even though they're not technically vectors. That sign tells us about their directions, and so we can still add them together that way. I probably wouldn't solve it that way. I would do this. The net force is 4 because it's 6 down the slope and 2 up the slope, and the two 8 Newton forces cancel each other, right? So I would just do it that way. 4 newtons times 10 meters times cosine of 0, because that net force is parallel and in the same direction as the displacement, and you still get 40 newtons. So you can find it either way. Once you have the 40 newtons, though, to find the velocity, we do what we've been doing. Work equals change in velocity, change in kinetic energy. We know the mass. We know the initial velocity was 0 because it says from rest. And so we can solve for the final velocity. It goes from rest to having a speed of 8.94 meters per second down the slope. So there's a couple ways showing you how you can kind of process the value of work. Questions on that one? Yeah.
Go to the bathroom.
Yeah. All right. So those are lots of ways to think through. Hopefully by now the idea of using work and energy is becoming almost second nature to you. You've seen so many examples. But we do need to really quickly revisit the concept of power. We defined it on the first day of this unit as the rate at which work is done. And so we could talk about it being work divided by time. And the units are joules for work and seconds for time. But rather than leaving it in joules per second, we have yet another condensed variable here for a unit, not a variable, but a unit. And we use W for watts. And this does get a little confusing if you're not careful. The W in the equation is a variable, meaning work. The W in the answer is a unit, meaning watts, right?
Massive meters.
Yeah, so you do have to be careful that you're recognizing when am I using W as a variable in an equation, and when am I using W as a unit on a number to give me an answer. So this is the base equation. This is not the equation that College Board gives you, however. I think this is the most, like every book will define it this way that I've seen, that the amount of work done per time. They all will talk about this as the normal equation. This is probably the most common way you see it. For some reason, this isn't the way College Board represents it. All right. So it's not, it's not that much different though. We spent the last half hour on the work energy theorem. So we can replace work with
What's
Delta energy.
yeah, the change in energy. The amount of work done is the change in energy. So that's the way College Board gives it to you. So this equation is fine, helpful, not necessary really. What they give you is close enough. This in red is what they give you. Change in energy over time, which is work over time, right? Work and energy, work and change in energy would be equivalent. But here's another one that's sometimes helpful. If we think about work as force times displacement, that's parallel, we get F times D over T. D over T is velocity. So you can also find the power used by taking the force applied times the change in velocity. Sometimes that doesn't make sense. Other times it's very helpful. So this is one I actually would suggest you put in your list of equations College Board doesn't give you that can be really helpful. You could figure this out without using P equals FV, but if you remember P equals FV, it can shortcut your time, all right? So very beneficial, highly recommend that you jot this one down.
Is that change in velocity or just?
It would be the change in velocity because it's the displacement over time, so. Could be the average velocity too, that would also work. You gotta quit using the word work when we're talking about work. That would also suffice. All right, some just common examples of, oh, did you need that again? Yeah. Good.
Yeah.
All right. Anybody else need it? All right. So just some common examples of where you would see this on a light bulb, 60-watt light bulb, using up 60 joules every second. Microwave, 1500 watts, using up 1500 joules every second. If you've got a clothes dryer, might be 4000 watts if it's an electric clothes dryer because it's heating and spinning with energy, so 4000 joules per second. So you would see a lot of devices around your home with watt measurements. All right, we're going to practice some problems here. So worksheets 3 and 5 are over here on the side. If you haven't picked those up before, we're going to take a look at those. If you are in the Zoom for U4, you can find it on Unit 8 in Topics, Worksheet 3 and Worksheet 5.
I just picked up a random one. Read 3 and 5.
3 and 5.
Oh no, there's no pictures of this.
So we're going to divide you up and have you solve a variety of different problems here for practice. We probably won't have a chance for all the groups to teach their problem today because we have several groups, but we should be able to get through a couple of them, and you should have time to finish solving it. We just may have to finish sharing your results on Monday. So we are on worksheet 3. we'll look there first. Worksheet 3, question 1. Question 1 is about a volleyball, and it's going to be assigned to, let's have Rocky and Sally. You guys have the volleyball question on worksheet 3, okay, number 1. And then question number 2 is about a roller coaster. And so for the roller coaster, let's have Evan and Andy, let's have you guys do the roller coaster question number 2 on worksheet 3. All right.
We got this.
It's the hard one.
I mean, it's got big numbers.
Then we're gonna
so.
skip to question 4. Johnny and Aiden, let's have you guys do question number 4, the killer whale question. All right, so you guys have the killer whale. And then let's switch gears to worksheet 5. So worksheet 5, let's have Nat and Kyle, let's have you work on question number 2 about Jack and Jill up the hill. Okay, that's your question, number 2 on worksheet 5. And then Ethan and Cade, you guys have question 3 about healthy and bulky.
All right.
All right. Everybody know which one you're doing?
Yes, sir.
All right, let me get some breakout groups here for you guys in
Let's
Zoom
get
so it's
cracking.
easier for you to communicate and share. Be prepared to explain your answer, teach the class. And so have a way that, discuss who's going to explain which parts and how you're going to display the work. All right. So for you guys in the Zoom, your breakout groups are ready.
Would 8 million joules be either this?
And then when Jack comes back, we'll have him join in with you guys here in the front row.
Okie dokie. Either 8 million joules will be disposed or be basically 8.
Yeah, would be the loss for A. Would be
8 million.
Yeah, we got big
Those
numbers.
big
Oh,
numbers.
yeah. Average magnitude of the pre-time track. Would just be divided by the well, from joules to meters, joules divided by 4 centimeters. So yeah, 8 million divided by 8,000.
Wait, so as hard as what I think.
What is the length of the track?
What is the length?
Pretty sure it's 100 meters. Right now.
Let's just say 2 miles. Divided by 80,000.
I have to put this in the calculator.
So would that just be the length?
So that's the answer.
We're you done? Let's go.
We probably should write down what we did.
Oh yeah, you're right. What
What's
did we
the
do? We just kind of did it. So 8 million was disclosed.
What's
Just for getting variables.
For power,
Yeah, for power.
8 million was
Capital
disclosed,
T.
and then we took that 8 million.
that's actually one that makes sense.
Yes, it does.
One of the few.
We divided up by 80,000.
It started out all nice. We had V for velocity and A for acceleration, T for time, and for mass.
Slowly.
And then it was all downhill.
Yeah, let's use P for momentum and L for angular momentum.
And K for constant.
It's
And
max
we
gravitation,
ran out of
right?
English. Let's start using
Beginning is
Greek.
like just
It'll be
ordering
great.
back gravitation.
And it's, you can write 50 million if you want. And then over here, we have kinetic energy. 32,000. So for 2 million. Then the rest is lost.
And then the system is just the track and the cart. I feel like we need to
There's
put
train
Earth too.
movement.
So we should put Earth too. or-
Train. So train there's gravity and the track and the air are not particles. So
Ah,
dissipate.
it's dissipating on the track, so we'll put the
Yeah,
track in
bull.
the thing.
No, we don't put it in. will be work.
Dang.
What's our group for number 2?
I'll just follow along with what you guys do.
Cool. Man, it's just a lot easier. Big numbers doesn't always mean a hard problem.
So question 1, that was the group online. That was Sally and Rocky. So you guys have question 2.
Yes.
You ready to start putting things up?
Sure.
Okay, go ahead and do that.
My big numbers.
Yeah. So much energy, I suppose.
Well,
Let's see what color.
I would fill this thing in first.
Oh, you're right. So what color should we fill this in?
Ooh,
Black.
the
Actually, yeah,
colors-
you could fill it in and then I'll do the rest.
The colors.
You wanna do something?
Sure.
Or you could write the system flow thing.
You guys can write
You guys
two at
doing
a
all right
time.
in here?
Huh?
You can both write at the same time.
Oh, I forgot. It's late.
Any questions, Tommy?
Oh, wait.
Actually, okay.
Wait,
What
can
color?
can we actually or no?
What color?
I know you can't.
Hmm.
Oh, it's,
You have to click the like arrow thing.
yes, it's in.
This thing is kind of.
I think you can only get one at a time.
Yeah,
Oh,
on that if you.
wait,
that's
it's
not
like
epic
the
then.
It'll be the same color though, right? Like, can you draw at the same time?
Oh, yeah.
Oh, but then we have to both erase at the same time.
Just make sure you take a screenshot of it, because the whiteboard doesn't say when you come out of the breakout.
How do I go back?
Just click on the pen.
Well, you just can't take a loss.
Oh!
Oh, then yeah.
Wait.
It's fine, just leave it.
No.
Wait, can you do this? Oh, we can't.
It appears not. Okay, hold on. So 50,000.
How are you guys doing?
I'm just gonna write this. Whatever you guys write down in here, I'm gonna write down.
Oh, that's just what I got.
Oh, beautiful.
No! 40.
It's
It's fine. No one's looking yet.
You know who used vertically answer seconds. So I was like,
Oh,
Yeah.
velocity.
Big number.
All right, I'm making sure I know.
How far along are you
There
guys?
you go.
Yeah,
How do we get
I don't
48?
know how.
It's 42.
Oh, 40.
Oh, I see.
It's 39.4.
And then we take.
And plugged in.
It's very sad.
Let me know if you need more help.
The sound, the sound.
No, I'm not very good at
Here,
this.
you want to erase?
Yeah, because if
Yes.
you did force times velocity, that's another way of doing it. So you
I'm gonna change color too. I just confuse
It's gonna be
everyone.
a two, just a two with blue.
Let's go with the sky blue.
Guys, use scientific notation. There's too many zeros.
Nah.
No.
This is cooler.
No.
So you guys ready
That
to
J
finish
looks like
Pokey
a happy
I
race zero.
Oh,
Okay. Are you guys capable of working on
There
this?
we go.
Yeah, we're.
That actually
And
looks
then-
better.
And then Hulky and Bulky, what did you get?
Sure, divide.
More powerful by about
By what?
100 meters.
1.5.
Wait, what? Oh.
So this is the answer.
Yeah, but we gotta show the equation.
This is the equation.
No, that's the math. We gotta go.
I might have done
E.
something wrong. Oh, that's a decimal point.
I feel like it wasn't the
Oh, yeah, man.
epic.
I did.
And then, oh, wait, here.
Well, let me just
Oh.
fix this a bit.
Okay.
So I might be drastically off.
Wait, what equation do we even use for that?
I was like,
I don't know, but we got the answer, I'm pretty sure. What color should I?
Was
Yeah, I'm kind of feeling
was the
green.
cookies right?
no.
Okay.
You must have the same thing.
Rethink this, yeah. Oh, yeah. Oh, I did 9.81 on the calculator. That one I wrote.
Wait, no, it's.
I didn't do. All right.
Wait, no, we didn't finish. Wait, did we finish? I don't know.
Oh, yeah.
I don't know.
That's a lot more watts.
No, because we didn't.
6.5 watts
no,
is
we're
very
not-
easily.
You were at
100.
650 and 490.
No, because look,
Okay.
there's
That makes
drag.
a lot more sense.
Nah, drag doesn't exist anymore.
We didn't calculate for drag.
I think we're pretty much done.
It's okay, drag doesn't count. We got it right.
No, I think we did it wrong.
We probably did.
Because we forgot the drag.
Well, that's a problem then.
How do we do
Oh,
the
yeah,
drag?
decimal points are just off.
Mr. Webb,
Mr. Webb, we forgot the drag.
so I'm gonna change the color again.
Times B squared. Okay, so friction force and drag is dV.
Oh wait, we need this. Oh yeah, didn't you run through the system flow?
What am I doing?
Just write
I'll do
train
it.
and
It
earth.
doesn't matter.
Yeah, just, I don't really
You
care.
guys
Okay,
didn't
you
do
should.
it. I'll just watch. Wait, okay, but I don't think we finished right. I think,
Wanna
I
write
think
Earth
this
then?
answer's wrong.
It probably
Because-
is.
Because we forgot drag.
So,
Drag.
so to find
How do you do it?
combine, combine drag, so if we find friction force, then we just subtract
Wait,
that
hold
from
on. This
80,000
is
newtons.
the
and
drag.
drag.
The drag has already been calculated.
No, but how are we gonna get friction?
How do you, well, we have 8,000.
Powerful bulky.
We never use that. That's probably a problem.
But we don't even have the friction. Coefficient.
Coefficient of friction.
I was going to.
Wouldn't the friction coefficient be
Yeah, my
Use this is how much.
Actually,
it-
force times displacement is just
velocity.
12 times 10 times 10.
Yeah.
The combined drag and friction forces is 80,000.
So,
But
it's
that
not people in
it
that
rolls
drag,
down the hill.
so.
Yeah.
Yeah, so if you,
So-
wait, Mr. Webb, drag.
It was
Yeah.
What do we do?
Did we do something wrong?
Well, it's the drag and friction are together, so you just have to have air
So
here.
how are we gonna get the length of the track? If we can't find,
Oh, yeah, force.
Earth, air, fire, water.
it doesn't matter.
Well, how are you finding it? Tell me how you're finding it so I can tell you what if you.
Well, we
just kinda
we
did-
found the loss.
The DED.
Yeah, so then we forgot about the drag, so we thought it was just friction.
Yeah, so then we just
How
divided
did
the
you-
80,000.
I think we divided by,
We divided 8 million by 80,000 to get the distance.
Uh-huh.
But
What equation are you using here? What's this? Like, what, they're just randomly picking a couple numbers and dividing them?
yeah,
Perhaps.
basically.
Yeah, I need more than that.
We,
dang,
we could have
this
used.
is unfortunate.
Could have used.
Wait, so let's just do that really
Work
quickly.
equals-
Mr. Webb, can I check my new and improved decimal pointed answers?
Yeah, looks good.
Awesome.
Nice.
I was off by like 100.
Dang.
And the force, oh my,
It's 80,000.
8,000, and the work.
8 million.
8 million joules.
Would it be?
Yeah,
Oh yeah,
so,
because
we did, we divided.
Okay.
This is what we
let's
did.
go.
I just want to make sure you knew why.
But-
You just
but
randomly
drag-
say,
but-
oh, let's
but
divide and see what
drag-
happens.
Yeah, what about drag though?
The
Drag
units
matter?
line up, it'll be fine.
It's around the right number, so you know.
Yeah.
So I was right.
Raised it together.
I was
So
right.
that's right.
Yeah.
Let's go.
That is great to know.
If someone asked for physics scholars, because
Uh.
yeah.
We got these fools.
All right, so
Yeah, that's a nice happy face though.
That is a nice house.
let me, I think we probably are only gonna have time for one or two to go, so we may just have them go since they're just written.
Should we rewrite it?
And because they just figured out how to do their problem.
Is it really? No, we had it done, we just didn't know why we got it right.
See, that's just how good we are. We don't
You don't
need to know how to get the answer.
You
We
don't
just
need
get it.
equations.
Yeah.
Just like.
Do you have a screenshot of?
Yeah,
You
mine
guys
is-
have a screenshot of yours?
We're just too good at physics. It's just the only
All
logical
right, how do you guys tell that?
explanation. That's just the only logical explanation.
I think we should work in.
Explain the rebound.
Well, work is
No, that's
more
max velocity squared.
It's
Easily.
Final
Think of one
one half first max velocity squared minus the initial one half max velocity squared. And we don't know the initial or the final.
Just on.
I think he's just really he's moving it at a constant speed.
Cool,
Epic.
that helps. It's in millions.
Wait, we should put proper, what's it called? The M thing. Oh, that's an M.
Units?
Yeah.
Oh,
Wait, it's supposed to be cat. It
oh,
works.
for 50 million?
And that's 0, it's fine.
Well, it's our Jules is already there, so.
Yeah, it's fine.
How did time get away so fast?
Time flies when you're having fun.
Apparently.
We use some pretty nice colors.
We got it like randomly just changes.
We got like the grapes on the bottom, and we just got red and like sky blue.
And green.
Yeah.
Green just comes out of nowhere.
But it is a mess.
You can see what we started with. We started with the red.
And then the pole.
Yeah.
Did you really do long division for 8 million divided by 80,000?
I wanted to. I wanted
Alright,
to display
so-
what we did very easily.
Yeah, I put it into my calculator.
Okay, we've only got a couple minutes left, and I want to make sure that this group gets, since they have it on the board already, want to make sure we get through this group. So we're going to start with question number 2 from worksheet 3. And that's probably all we're gonna have time for today. So we'll have Sally and Rocky, we'll have you guys start back on Monday with your problem, and we'll finish them up Monday. But let's get through this one. We got a roller coaster starting from rest, rolling down a hill, storing kinetic energy of 42 million joules at the bottom of the hill. If the train earth system stored a total of 50 million joules of gravitational potential energy at the top of the hill relative to the bottom, how much energy is transferred from the train to the track and the air as it moves down the hill? If the average magnitude of the combined drag and friction is 80 newtons as the train rolls down the hill, what's the length of the track between the top and bottom? So go ahead and talk us through how you solve this. Each of you can give a little explanation of some part.
All right. Want I go first? Or?
Okay, so we took the 50 million joules to 50 million joules to start off with, and the 42 whenever it's at the bottom, and we just subtracted them to get the work done, which is 8 million.
Yeah, then basically we use the work equation, force times distance, and solved it for the distance and divided. Oh, he's gonna have nothing left to explain.
the graphs.
Yeah, that's good.
Okay, so then we divide the work, which was 8 million, divided by the force, which was 80,000, and got 100 meters.
And then I came in late, so I'm doing the graphs.
Yes,
There's
graphs. I
50
know about
million,
graphs.
50 million joules, and then the other one is the 42, I think.
Yeah.
And then the bottom is that final position. Yeah.
The 8.
Yeah.
All right, so train, earth, air.
Should have been the track too, but
Yeah, so we just,
but at the top it said if the train earth system, so I wasn't sure.
yeah. So so the train and earth system would be the gravity, the air and the train would be air resistance or drag, and then the train and the track would be the friction. So we would want to add track into our system flow there.
Should I add it?
Sure, you can go ahead and do that.
Hey.
Well, no matter, you're gonna erase this.
Let's go with another.
But yeah, I
color.
am gonna erase it here shortly. So.
New color.
All right.
There we go.
Yeah.
Any questions about this problem? Can you guys see it okay? I don't know if did I even share it?
Everyone is so confused that they don't have.
I don't think I shared it, so you guys probably have a hard time seeing it.
Oh, if it wasn't shared.
Maybe see it through the camera, but now you should be able to see it a little bit closer. Lots of color. All right, so we're going to come back to this on Monday before we start momentum and finish going through some problems. I want to make sure that we have a chance to review. It'll be good after the weekend to refresh our memory on this anyway. So bring that work back, and we'll have the other group share. For the 4 of you in Zoom, good to see you today. Hope you have a great rest of your day and enjoy the weekend. We'll see you on Monday.
Thank you.
And for you guys in your normal routine, we'll just pack up, wipe down, get out. Enjoy your lunch. Get low here again.
Oh yes, the clear windows. My favorite.
I didn't hear what their final recipe was for this.
It's really weird. It's kind of scary.
Sodium.
I know they talked about
It says it's
peroxide and
it's
alcohol.
it's like 4% hydrogen peroxide and 96% other. And then it has all these warnings that it's like if you touch it, you should wash your hands for 20 minutes under clear water, and if it gets on your clothes.
What is this other?
It's really scary.
Miscellaneous.
All right, I'm now gonna
We
put.
touched it so many times.
I know we're all gonna die.
I'm now gonna use 5 paper towels every time. Touch my skin.
Yeah, I believe it's mostly alcohol and hydrogen peroxide and water. I don't know of anything else.
What the other fish?
I know, why don't they just say water if it's water?
Maybe they just don't want people to know it's water.
They want
You're welcome.
to make it look like they're complicated.
Do you have a question?
Yeah, just one from.
So you must see you. Have a good weekend.
I was struggling with it because I was thinking forces, but then I was thinking like the centrifugal motion with this one, and then I just
All right. So
I did pretty good at this one. I loved it at the last one, but
students trying to determine the minimum height from which to release the roller coaster so that the cart completes the loop without falling off. After the question, answer the question for the case. The cart barely loses contact with the surface of the top of the shot. The life backwards friction drag inside. Okay. What is the cart's acceleration at the top of the loop? So at the top of the loop, if it's got
the reason why I put zeros because I assumed they dropped it. They just like sit it down and then.
they're talking about here at the top of the loop.
Yeah, that's what messed me up though.
Oh,
When I saw top, I didn't see the loop for these two.
Oh, okay.
So I was assuming up here, and I got really confused.
Okay. So the way that I would set this one up is that you know that the initial energy that it has is going to be all mgh, right? Because it's starting with just gravitational, and then in the loop it's going to be mgh plus 1/2 mv squared, because it's got both kinetic and it's also got gravitational. And so did they give you the mass? I guess it doesn't matter, the mass will cancel.
Oh yeah, this is called the mass of the cart and the mass will cancel.
Yeah. So here's m, those cancel. And so we've got GH minus GH equals 1/2 mv squared. So we've got, this will be 0 then, equals, oh no, we have a different h, it's not the same. Because at the beginning it's h. It's g times h, and then minus g times, it has a number, doesn't it, for the height at the top of the loop?
For the top of the loop, it's 14 meters.
14 meters. And it doesn't give you this height though, right?
No.
Okay. Equals 1/2. So B would be 2 times H minus 14. So this is just 10. You know that.
So like 10H minus 140.
Yeah. So we've got 20H minus 280, right?
Yeah.
And let's see. They don't give you the height at the top though, right?
That's what the loop to do, but not on top of
But
it.
not at the top. No. Okay. And what's the question one again? What's the velocity?
It's what's the car's acceleration at the loop over here.
Okay. Oh, the acceleration. Okay. I think I was thinking of a different scenario. So if we want acceleration, then the acceleration is going to be v squared over r because it's centripetal.
Yeah.
Right. And the centripetal acceleration there, it said it just barely makes the loop.
Yeah.
Right? Yeah.
At top, they said it's starting to fall off. So.
Yeah. So what they're saying is that the mg, like the weight of it, is going to equal the mv squared over r. Because it's the weight force is going to equal the centripetal force. They're balanced. So again, the masses cancel. So v equals gr. Did they give you the radius of the loop? I guess it's 7 meters, right? Because they tell you the height.
I think so. Yeah. It's 14 meters, so yeah, the radius would be 7.
Okay. So if we put this over here, we got the square root of 20h minus 280 equals v, which is equal to square root of gr. And so this would be square root of 10 times that. So then all you have to do is find the height. But is that what they asked, how high to drop it from?
They have to add, that's what they're asking, yeah, they were, the big question was, from what height must the car be released? And some other questions were, what's the car speed top of the loop and what's acceleration top of the loop?
So it doesn't ever ask you how high it's dropped from?
It does.
Oh, it
ask
does,
you
okay,
that
so
one.
that's how you'd find the height. For the acceleration, let's see, we don't know the velocity, but we can find the velocity because we know this. And then once you know the velocity, you can plug it in there to get the acceleration. So this would be how you would find the height. This would be how you'd find the velocity. And then this answer gets plugged into here to find the acceleration.
Okay,
That's how I would solve it.
okay, well, thank you.
Yeah, if you want to take a picture of that to review it when you have a chance to look at it, you're welcome to. Unless that makes sense.
It makes sense,
Okay.
yeah. But I also think I have to do some work to it with some typical motion.
Yeah, it's been a little while since we did that, so.
Yeah, and also I wasn't I didn't do very good on that
That was
section.
a weak
I was,
area
yeah, I
for
was struggling on that.
Okay,
Okay. Thank you.
you're welcome.
Bye.
See ya. Have a great day.